Hi. This is the most dramatic entrance. All right, cool. Hey, everyone. And this is the end of Google Developer Day, I guess. Hopefully it's been good for you so far. And I'm going to give a talk, kind of an advanced talk, about the Maps API, giving performance tips for improving your mashups. And the reason I want to give this talk is because at Google, we think that latency and performance is really, really important. And we consider these one of our top priorities whenever we're doing anything, to the point where if something isn't fast enough, we simply won't launch it. And our theory is somewhat that if your website isn't fast enough, the user isn't going to use it, they're not going to buy your product, they're not going to click on your ads, they're not going to do whatever useful thing you want them to do with your application because they'll be too frustrated. So we want to help developers make their websites as fast as we've made our websites and help you guys have that same standards for your performance. So one of the things that causes mashups to be slow is the actual loading of the JavaScript API before you do anything else, right? And the reason that it's slow is that one of the reasons it's slow is because there's just so much to load, right? So you have lots and lots of images to load to make the tiles and the markers and the controls. You've got lots of JavaScript to load, like the Bootstrap, the main library, the copyrights JavaScript, the modularized JavaScript. So just a lot of stuff to load, and it gets slow. So if you look at the actual load sequence, this is average on a desktop browser. And you can see it takes about 4.6 seconds until the tiles are actually shown. Now, this is kind of OK on the desktop. But now, if we look at those same times on a smartphone, oh, it's not that smart, I guess, but iPhone or Android, you can see that it gets a lot slower. So it's nearly, 4 or 5 times as slow until we see the tile. So you see 18 seconds. 18 seconds to wait for the map to load is basically unusable, right? At that point, they've given up, and they've just wandered off and decided to find something on their own. So one of the problems here is the fact that there's too many images for the tiles, right? Because the way that we achieve interactive maps is that we do tile-based things, which means that for any particular map viewport, we're probably loading in about 9 tiles, because we're loading in all the visible tiles, and including whatever is overlapping, and then sometimes also loading in buffer tiles so that when you pan, it's a smooth experience. So that can mean a lot of images that you're loading to start up. So one solution here is to use the Static Maps API, at least from the start. So I'll show you an example of that. So here, when I load the page, it's going to start with a static map and then turn into a JavaScript map as soon as it's ready. And you actually saw that transition right there where it went from static to JavaScript. So the advantage here is that the user sees the map as soon as a static map is available. And by the time they actually want to interact with the map, hopefully all the real interactive tiles have loaded in, and it's a good experience for them. So this is something that developers have been doing for the past year since we've launched the Static Maps API to make their maps appear faster, right? So basically improving the perceived latency for the users. And this is something that you can do as well, but it does require a good amount of coding in order to make the transition be as seamless as possible and to make it look the same as the static map. Another of the problems we have is just that the JavaScript code is too big. So I've highlighted all the classes that we added to the API since I started at Google 2 years ago. So we added a lot. I'd say we actually tripled the size of the API because some of these classes are pretty fat classes. And this means it's about 220 kilobytes unzipped of JavaScript. And if we look at how long that takes to parse on the iPhone, the iPhone is a bit slow at parsing JavaScript, and it ends up being 4.4 seconds simply to evaluate this JavaScript in memory. which is really bad. So what we tried to do on our side at Google to make this problem better for you guys was to modularize. So about a year and a half ago, we started modularizing a bunch of the classes in the API. So we modularized the controls, we modularized polygon, polyline, a few other things, which basically meant that we would have stubs of those classes in the API that you downloaded at the beginning. And then once you actually created a polygon object, we would go and fetch a module that had the rest of the code necessary, so that basically our initial download for the JavaScript was smaller, and you didn't download JavaScript that you didn't need. So we managed to shave off 40 kilobytes from our 220 kilobytes, but that still leaves us with 180 kilobytes that we couldn't get rid of. And it was really hard to modularize the API since we hadn't designed it to be modularized from the beginning. So it ended up causing various bugs and problems. So yeah, right now, if you want to make the JavaScript faster, you could start with a static map, and we could keep trying to modularize the JavaScript, but we kind of gave up. So we've decided to start from scratch and rewrite the JavaScript API. And we announced this last week at Google I/O, JavaScript Maps API version 3. And it's completely rewritten API. And its whole goal is to solve the problems that I just showed you, so that to make it easier for you guys so that you don't have to be doing this yourself. So if you look at the speed comparison here, this is on the iPhone, right? So V2, 18 seconds. V3, we've gotten down to 7 seconds, and hopefully we can get it down even more. And V3 is also significantly smaller. It's about 35 kilobytes unzipped right now, compared to that 180 kilobytes unzipped from V2. And the way that we achieved our latency improvements in version 3 is, first of all, is that we do the static map optimization for you. So when you create a new map object, we'll always start that map with a static map and then load in the tiles after. And we'll also make that static map even feel interactive, right? So you as a user don't even realize that there was ever a static map there to begin with. So that's how we improve the perceived latency for users. And to improve the problem of having too much JavaScript, we've written the new API using an MVC architecture. MVC stands for Model View Controller. So basically the theory is that we have these models, and the models are what you actually download in the beginning, right? And then the views are what you download later once you actually use those models. And this is really good for a JavaScript API, because if you have a map, right? A map has a lot of properties on it. It has a center and a zoom and a map type. And you can get these properties and set these properties and listen to when these properties change, right? And that's not that much code to define a model that has a bunch of properties. Very small amount of code. What is a lot of code is actually creating a map, and creating a map that works across all these different browsers, right? So that works in IE, Firefox, Safari, Chrome, WebKit Android, WebKit iPhone, all right? So that's the view, and that's what takes up so much code, is all this JavaScript and HTML and CSS creation. So what we've done is that when you download the initial API, you're simply downloading the model, and once you create a map, that's when we go and fetch the view for the map, and then load that in, right? And that's where the bulk of the JavaScript is. So we have models for map and for marker and for info window, and basically everything in the API is a model, so that you won't actually get any code that you're not using. So this has allowed us to have basically, hopefully, scalably small JavaScript. So even as we add more and more classes to the API, we're still only adding the models to the core API, and the views will always be modularized. And we've also cleaned up a lot of code since we started from scratch. We can look at code and be like, well, we don't need this, we don't need this. These were too interdependent on each other, let's untangle this. So generally, we've gotten rid of just code we didn't need. So that's how we got it to be so much faster. So here's just a hello world to show you what it looks like. It looks pretty similar to V2. It's always going to be in a namespace, so it's in the Google.Maps namespace. You can use V2 with that namespace now, but this one is just always in it. And we do use object literals a lot for passing in the properties, and we're using that. We used them in V2, and we're using them even more in version 3 because they're so flexible. But that's it. It looks pretty similar. And when we actually look at what a map looks like from V3, here it is. It looks just like V2. So you maybe can't tell the difference, but it is significantly faster, and you can try it on your iPhone or on your Android and see how fast it is for you. We do have default UI enabled all the time. So just the UI from maps.google.com, and you can disable this if you want. We do try and resize those controls smartly. So if you're viewing this on a small phone, we'll give you smaller controls. If you're viewing this on an Android, you'll actually get a special Android-looking zoom control. So we are trying to do things that are kind of smarter and more targeted towards small screens and mobile devices. So V3 right now has a limited set of features. So we have markers, controls, info windows. We have one service, which is geocoding, forward or reverse. And we also have a custom overlay interface. So if you want right now, you can create ground overlays. You can create custom info windows or markers for your site. So it has such limited features because we launched this API in labs, which means that it can change at any time, and we want it to be able to change because we've launched it early so that we can get your feedback on the features that we've created now. So we hope that you'll go, home tonight after the party and go use it and see how easily you can, make your site with it or port your site over and see what problems you encounter and see, how it works on your mobile phone and see what you think about the design, and then give us feedback, and then that will affect how we do the API. And then once we've gotten enough feedback from people, then we can consider making it be a non-labs API and committing to backward compatibility. But right now we're taking the most popular JavaScript mapping API in the world and rewriting it from scratch. So we don't want to make a mistake, because then we have to keep it around forever again. So if you guys can go and use it and tell us what you think, that'd be really fantastic. So that's solving the problem of loading the JavaScript API. So there, we actually decided that it was too much work for you guys to solve it, and we needed to take matters into our own hands. But there's still other problems that you guys are going to encounter that you can do the solving yourself. So one of these classic issues is displaying too many markers. We'll often have people come in the forum and say, I just tried to display 10,000 markers on the map, and my map got really slow and my browser crashed. Why? Well, because 10,000 markers is a lot of markers to display, and honestly, the problem is that the gmarker class was not designed for being on the map 10,000 times, okay? So the thing about our API is that our API is based on Google Maps, the consumer product. It's JavaScript. So if you think about Google Maps, the consumer product, when you do a search there, you get back 10 gmarkers, right? So these markers are designed to only show 10 of them at a time. And they're designed for features. So you can drag those markers, you can print those markers, you can roll over different parts of those markers, and it works across every browser, including IE6. So all kinds of features like that, which means that one marker is in fact possibly up to 5 DOM elements, all right? Because we have the foreground, the background, the image map, the shadow, all these different things, right? Which means that when you display 10,000 gmarker, you're actually putting 50,000 DOM elements on your map. And 50,000 DOM elements to a browser is just hell, right? It doesn't want to deal with that. So the solution here is that you should design your own marker that has the features that you need and performs the way you want it to perform. All right? So we have the ways of creating custom overlays in all of our APIs, and so that you can create these light markers yourself. So I'll show you a little comparison here. So, I'm cheating. Don't look. All right. So here's gmarker. I'll add 500 of these. We'll wait. OK? So here's 500 gmarkers. That actually went faster than when I did it before. I think it's cached a bit. I'll try and pan the map. It's a little painful. Let me clear these. OK. Now I'll go to my marker light, which is my custom class. Add those. You can see that was a lot faster. And also the panning should be smoother as well. Yeah. So gmarker is about 5 DOM elements. Marker light is only 2 DOM elements. I've got a div and then an image node inside of that, right? So that's how I'm able to achieve a little over twice as good performance. So that's one thing you can do. Now, you can go even further than that. So we have a real estate site called Redfin, and they wanted even better performance than this. So they created something they call a supermarker. So I'll show you how this works here. Let me do a search for, let's say my maximum will be 550,000, because I'm just rich like that. And so here you can see we've got nearly 500 markers on the map, and they displayed really, really quickly. So it's actually even better performance than my marker light class. And let me do a little deep dive to show you how they did this. So here's how you create a custom overlay. You simply extend our GeoOverlay class. So here's the constructor for supermarker. You can see it's simply going to just hold a div inside of it. And when we first create the marker, we're just going to create one div for that whole marker. So basically, step back, what we're doing is before, with marker light, when I wanted to add 500 of those, I would add 500 marker light overlays to the map. And then the Maps API would kind of take care of what would happen when the map panned and zoomed. What we're doing here is creating one overlay. We're going to add that to the map, and that one overlay is going to have 500 divs inside of it. And we're going to take care of removing markers from that one overlay. So we create a div, and then we append it to a pane in the map. And whenever we want to draw this, we have an array of latitude, longitude points. And we iterate through that array, turn it into pixels, and then just write out divs for every single thing in that array, and then append that div to our one supermarker. There's a couple other little performance enhancements in here. Something you should know is that string concatenation, when you do plus equals to concatenate strings, that's actually slow in some browsers like IE. So instead of doing string concatenation, it's better to do an array, push onto the array, and then do a join. So there's a little tip for you. Another thing to know is that it's faster to do inner HTML set to a massive string instead of doing constantly using the DOM API. So instead of doing document.create element, element.style.left equals blah, element.style.background color equals blah, document.div.append child blah. So that can get really slow for the browser because it has to process every one of your DOM commands. So it's actually a lot faster for the browser to simply make a massive string that contains these 500 divs and then just set that to the inner HTML of one div. So those are just general things that you can use for non-map stuff as well. And then when we want to actually use this supermarker, we'll just create a new supermarker, add it to the map, and then we can just draw a bunch of markers into that supermarker and then remove them and add them as we need. So this is basically taking it to the max of performance for custom marker overlays. And that was for the JavaScript API. I haven't mentioned the Flash API yet, but Flash actually also has a DOM. Flash is generally more performant since it's a plugin, but it has a DOM, so the more you add to the DOM, it will also suffer from performance. So people in the Flash community went ahead and made their own supermarker as well, which basically looks exactly the same as that, but in ActionScript. So I'll show you this demo. So here we go. This is a Flash map, and just showing the victims of some really evil guy named Madoff. So you can see there's thousands of pseudo markers here, pretend markers, and we can mouse over all of them and still see tooltips and colors and all of that. But it's really, really good performance and loads very fast. So you can do this supermarker technique in JavaScript and in Flash, or you can just take the marker light technique, which works pretty well. The thing to just consider is the amount of DOM nodes. Now, even this technique can fail if you have 60,000 points of data that you want to show on the map. 60,000 will just simply be too much for however many, whatever of those techniques you use. So in that case, you want to think of ways for reducing the number of DOM nodes, right? Reducing the amount of data you have to show. So one technique is clustering. So I'll show you some examples of that. So author mapper, this is a classic example of clustering. Let me zoom out here. All right, so you can see what they have is we have markers that represent individual data points. So we can see there's one article here. We have markers that represent multiple data points. And then when we click on those, it'll go and zoom in and break out into more clusters. And then we also use the color on the markers to indicate how many data points are in a particular cluster. So you can see red is actually the most number of points here. And here's another technique. Another example, so this is a site that maps panoramas in Prague, and they've got a lot of panoramas to show, so they had to do clustering. And they do a couple different things with the user interface here. So they show numbers on top of the circles to show you how many things are in the clusters, and then give you the option to zoom in to see more. So the general technique for clustering on both of these sites is that they have a bunch of data, and every night or every week or every month, they'll go and run a clustering algorithm on that data on their server, and then write out cluster information to the database. And then in JavaScript, all they have to do is load in the information about the clusters and then show that on the map. So this is a great technique, but it does mean that you need a server to run this. You need a database to store the cluster information in, and you need to write an algorithm. And I don't know, sometimes it's hard to write algorithms, depending on how long ago your computer science classes were. You could do he just made up this algorithm. You could do a k-means clustering algorithm if you wanted. That was always my favorite in class. But it is a fair amount of effort, right? So it is possible to do clustering in JavaScript. So we released this library a month ago that would do completely JavaScript clustering, which is nice because it means you don't have to do the server, the database, the algorithm. It's all done for you. So this uses a really simple clustering technique. It just divides the world up into a bunch of 80 pixel square grids at each zoom level, and then makes clusters out of them. And then just does that as we zoom through the different levels. But the cool thing is it's just really easy to use. So we have a bunch of G markers, and we can just pass that array of markers and the map to a marker cluster, and then it does it all for us. This is an open source library. You can tweak it. We've already had one major modification to it. And I think people get really excited by it because it's just so easy to use, and it gets rid of a lot of the overhead that server-side clustering has. But the thing to keep in mind is that since you are doing the clustering in JavaScript, JavaScript is pretty fast these days. But if you're going to do a clustering algorithm on maybe 10,000 markers, that might be too much, or maybe 20,000 markers, that might be too much. So you have to consider the maximum of markers or data points you might possibly ever have in deciding whether you would do a server-side clustering or a JavaScript clustering route. But certainly start with this. So this is just kind of grid-based or clump-based clustering. Since we are doing maps here, we can do regional clustering. So in maps, we divided the world. We've all decided in the world that we would divide it into political regions, and we would kind of made a hierarchy of those political regions. So we have notion of continents and countries and provinces and states and cities and boroughs and suburbs and postcodes. And we kind of have this idea of this nested hierarchy of them in our head. So this actually lends itself really well to clustering, because at zoom level 0, when you're all the way zoomed out, that's when you can show the continents. When you zoom in, that's when you show the countries. And then you zoom in more, you show the states. Zoom in more, you show the cities. So here's one example of that. Let me zoom all the way out. So this is Traveler. And they're basically like Yahoo Answers, but for maps. So you can see when you begin, they're basically showing continents. So I can see there's 125 in Asia. And then I can zoom in, and it'll show me that I guess I should do Japan since we're in Japan. There's 14 in Japan. They're an Australian company, so they have a lot more in Australia. And you can see, all right, there's still Kanagawa, yeah, I shouldn't pronounce them. And so then we go in and we see the cities, right? So this is really nice, a really nice technique. One thing you can do to make this better is I don't actually know what these things represent, like how big of an area they represent, until I mouse over. And then I still don't know unless I'm actually from this country. So I don't actually know if Shizuoka is a city or a province, right? Because I'm not from here. So what you could do is actually represent the region using a polygon when you mouse over. So these are state clusters. So when I mouse over this cluster, I immediately know that it's, well, I even did a tooltip there. So I immediately know there's 17 in Texas, and Texas is this area here. So probably the best thing to do is to combine regional clustering with showing the actual regions to the user so they understand what each cluster represents. So here's a few more clustering resources. There's an article that compares a bunch of solutions. There's some Python k-means code in case you want to do an algorithm. Maptimize is a hosted clustering offering. And so there you give them your data, and they'll go run it on their server and their database, and they'll just give you back some JavaScript to run on your site. And they will make you pay for it, but hopefully not that much. But everyone's got to make money some way. So clustering is what you use when you want people to eventually be able to drill down to the data and click on the data and see each individual point of data. But that's not always necessary. Sometimes you have a huge amount of data, and you don't actually care about people seeing each part. You just want them to understand generally what that data looks like on the map. So there you can do other types of solutions. So one solution is here, which is basically a visualization of the data. So here they plotted all of the campaign contributions in the United States, and you can see all the Republican and the Democratic, and you can break it down other ways as well. So this is really nice because I can go and drill down into wherever I live and figure out whether my neighbors are dirty Republicans or whatever, right? So it's good, and it just gives me a general idea of what I'm looking at, right? I don't really care about clicking on each individual. I don't care who this guy is right here, or this guy. I don't care about clicking on each of those individual pixels. I just want to have this general idea of what it looks like. And you can do a sidebar as well if you want people to be able to explore this. But this is basically an exploration interface. And sometimes you have data that you just want people to explore. Another thing you can do is actually use heat maps. And there is a heat map API that you can use. And here, this is an example doing a search for pizza in Boston. They've done a heat map of where all the results are. So this is good because I can look at this, and if I want pizza, I can immediately figure out where I should go and where I shouldn't go, just based on the data. So if I don't care about the particular restaurant and I just want to drive around, this is a good solution here. And with this site, I could eventually drill down and see the individual results, but this is just an option that they give you for the people that don't really care about those individual results. So there's an API you can try using for that. And the thing about the heat map is that you could also make it interactive as well. So this is a site called WalkScore, and what they've done is made a heat map that represents the walkability of neighborhoods. So you can see the green area is very walkable and the red is not. And you can actually go and mouse over this heat map, and as you mouse over, see statistics for each neighborhood. So this is a nice example of having a heat map and still having it be interactive. So the final example I want to show you for this is kind of a solution that both shows data density, but also is interactive and lets you click on each individual result. And this is something that Google Maps is actually, I think, one of the first ones to do. So here, this is Google Maps. Let me zoom out here. And I've done a search for sushi in Sydney. Sydney actually has a lot of sushi, which is why I live there now, because I like sushi. And it used to be when you did a local search in Google Maps, you would only see those 10 markers. And the users kind of didn't like that, because you'd see 10 markers and go, well, I know there's more sushi than that in Sydney. And you'd have to paginate through all the results, and you didn't really get this good idea of how much sushi there was in Sydney. So we came up with this solution, and we call them pimples or measles. I forget how they're going to translate that. But basically, we have the results, and then we represent the top 10 results, and then we represent all the other results on the map as these pimples. And then we can still click on these. So if I want to see what's there, because I actually work really near there. Oh, yeah, I've been there. I can go and click on that pimple there. Now, we could have done these as something like marker light or super marker, but we wanted to make sure that our solution would scale to however many thousands of results there were. So what we did instead was come up with a new solution. So the solution is that we take these are all rendered as tiles. So let's see, I can probably show you the images. Let me get one with a pimple on it. So here's one tile, right? It's kind of hard to see that, but that's one tile, and it's got three pimples on it there. So each of these are tiles that are laid on top. And then what we do in order to make them clickable is we pass down JSON. There we go. Let me go show that. So here's some JSON, and the JSON contains information about the clickable pixel bounds and what ID that clickable pixel bounds corresponds to. So what we do is that every time you move the mouse cursor, we're checking all the clickable pixel bounds that we know of, and we're saying, okay, which pixel bound are we inside, and should we turn into a cursor if we're inside one of those bounds? So here, it's just a mouse over that's just doing a check in all these bounds. And then when we click, we're checking to see, okay, which bounds are we inside of, and which info window ID should we pop open? All right, so this makes for really efficient performance because no matter how many results we have, we're serving the same number of tiles, and we're just increasing the size of this JSON file by a little bit. And really, JavaScript is really quite fast at calculating what pixel bounds a mouse cursor is currently inside of. So don't be afraid of doing checks in JavaScript to see what bounds you're inside of, or even what polygon bounds you're inside of, because you'll be surprised at how fast it is. You can really do it on mouse over events, which is amazing. So that is one way of doing it. There's one more here. So here's another example of clickable tiles. You can see as I mouse over, my mouse cursor changes over these little dots, but really these are all just tiles as well. So instead of doing the tiles and the JSON service, what he does, this developer, is he passes in tiles that have cookies attached, and as soon as a tile comes in, he strips the cookies off those tiles, and the cookies contain the information about the clickable pixel bounds, and then he uses that to determine the mouse cursor and the info windows and stuff like that. So that's even a bigger performance improvement because all he has to do is pass down the tiles, and he has everything he needs for a clickable tile. All right, so that's basically a lot of solutions for when you have the problem of rendering lots of markers. A very similar problem is when you want to render either very large polygons or just lots and lots of polygons or polylines. And this is usually when you have a bit more sophisticated data you're working with. And this is basically, we have the same problem that we had with gmarker. Our gpolygon in the API was not designed for performance. It was designed for features. It can be edited. Last 10 minutes, sweet. It can be dragged. It can be geodesic. It can be encoded, all of this, right? So that means that when you use it to display lots and lots of them in the API, it can get slow. So one solution, just like Marker Lite, is to do your own polygon class. So this is an open source polygon class created by a developer when he was working on the election maps because he wanted to be able to represent all the different voting districts fast. So this uses the canvas, the HTML5 canvas tag, and then also uses VML in Internet Explorer. And this right now is showing 34,000 vertices. And the awesome thing is that I can animate it. Well, usually. I have a lot of tabs open right now. Go. There we go. So here, you can have thousands of animated polygons, which you guys might not need. but it's awesome. So you should do it anyway. So it's very fast, and that's what you can do if you want to just replace gpolygon with a custom polygon light. But even so, you have the problem where a lot of GIS data just has too many points in it, because when people create GIS data, they're not creating it for web maps. They're creating it for desktop applications like ArcGIS, which don't really have the same problems that web maps do. So almost any time you get GIS data in a traditional form, like a shape file, you're going to want to, you're going to have a lot of points in it, and you can't display that many points on the map at a time, even using Polygon Light. So one solution is to think about how many points you have to display for a particular zoom level and for that particular viewport. So it might be that at zoom level 6, you only really need 20 points to represent the general shape of a line. And then at zoom level 20, when you're seeing this small portion of the line, that's when you need more points to represent it. But it may be that this line now is 1,000 points total, but in this viewport, we're only looking at 100 of them, right? So optimizing the number of points we're showing through in the viewport, since we do viewport clipping, will mean that you'll get better performance. So you can achieve this in the API using something called encoded polylines, which means that you create an encoded polyline, and it tells us what points should be displayed at which zoom levels, and then we'll take care of rendering the points at each zoom level. So you can look at that example. I'll go a little faster. So even so, you still might have the problem that these points, there's just too many of them, and some points are not necessary. So at the same time as encoding them, you should also be simplifying them. And the good thing is that encoding and simplifying are actually very similar processes, right? So you can use the same algorithm to encode and to simplify. Because if you think about it, if our maps actually went into zoom level 25, then you would need every single point, right? So we're always optimizing for the amount of zoom levels that web maps can display. So encoding and simplifying, very similar, use the same algorithm. So whenever you get your data, you should simplify it and encode it at the same time. So you optimize the total number of points that are ever shown, and also the number of points that are shown per zoom level. All right, so you've done all that, and your app works pretty good in Chrome or Firefox, but then you test it in IE, and then it's shit in IE, roughly. So the problem here we have is that browsers still have not agreed on vector graphics. Well, everyone else has agreed. So for most browsers, we can do SVG or Canvas. For IE, we can only do VML. So it means in every browser, we actually have a different way of rendering your polygons, which means you get different performance in every browser. So this would be an okay situation, maybe, if all of these had roughly the same performance. But since all of these have different performance, and some of them are good for animating, and some of them are good for having lots of points, it means it's inconsistent, which is the worst thing for a web app, because you want to have all your users have the same experience. So this is a problem that anyone doing vector graphics on the web suffers from. So one solution is to give up on JavaScript entirely and use the Flash API. And this works well because Flash was actually designed for vector graphics from the start. So you can see, here's an example of using Flash, and it's really, really fast. Since Flash, is just natively good at that. And you can see that there is actually an example where they do the same data with both JavaScript and Flash, and you can compare that in different browsers. And in Chrome, you won't really see a difference because Canvas is really fast and Flash is really fast. In IE, you'll see a big difference because VML is significantly slower. So that's one solution. Another solution that works in Flash, JavaScript, anywhere is to do tile layers. And this is a solution that Google Maps itself uses. So you can see these maps have huge amounts of data. We have highways and roads and rivers and all of that. And this is the problem that Lars and them had at the beginning when they're trying to figure out how to do maps on the web. And they figured out to do a tiling system, right? So if we go and look at maps, we have, here's Tokyo. So if we look at this tile right here, so I've got outline images on, so you can see this tile is one image. And when I double click on this tile and zoom in, that one tile becomes 4 more tiles. And then if I double click on this and zoom in, that one became 4 more. So the way that we load vector data in is we basically turn it into tiles at every zoom level and form this image pyramid of increasing resolution and load in more tiles that represent the more detailed vector data as you go in. So this is great because it means no matter how much data is in this, and there's a lot for Tokyo, it doesn't matter because we're always loading in the same number of tiles for each viewport. So we get consistent performance with tiles. And same with Flash API. You could use these tiles in Flash API too, and we do. So there's another example from a developer here. And he's just generating these tiles using Perl and a PostGIS database and just rendering out the tiles to his server. So this is something that developers can do as well for their sites. Now the thing about tiles is that they lack the interactivity that actual DOM objects have. So that's one of the reasons that a lot of people don't want to use tiles. But we can hack interactivity, kind of like we did with the pimples with local search. So let me show an example of that. Let's see. Here we go. So here, what we're looking at is a tile layer that represents the voting districts in the Pennsylvania primary. But as we mouse over this tile layer, we highlight which region we're over using just a native G polygon in the API. So this is nice because we're only showing one G polygon at a time to highlight the current area. And we're showing everything else using a tile layer, which is highly efficient. So we're taking advantage of the efficiency of tile layers, but still getting an interactive experience. So in conclusion, when you're looking at these problems that you might have and you're looking at the various solutions, because I showed you a lot of them, there's some things you should consider when choosing your solution. So there's how well it performs and how well it performs across different browsers and platforms. There's how interactive it is and whether the users can highlight things and mouse over and click on things and how much of a piece of data they can click on. And there's also how much effort it takes you. Some of these things take a lot more engineering effort than other ones, right? So for me, I would probably never render tiles because I simply can't be bothered to do that. I would probably pick Flash, right? That would be easier for me. But for you, if this isn't something you're going to invest in, then maybe you don't mind the engineering effort. So just consider all these things when you're thinking about what solution you want to do. And how much time do I have? A minute? 1, 2, sweet. I got 2. So now I will try and relate this to what I just talked about. How many of you guys are actual Maps API developers today? OK, great. So if you're a Maps API developer, and maybe you're a freelancer or you're working for an agency, and you want to make people know that, we just launched this developer qualification program. So you can sign up for this, and you do a test, and you provide references, some sample code, and list community participation. And then we'll tell you, OK, you're qualified. And then we'll list you in our qualified Maps API developers directory. And so we'll direct people that are looking for Maps API developers to that directory, and they can find you there. And this is a problem we've had for the last few years, is that people always ask us, we need somebody to do our Maps API mashup, and we've never had a good way of referring people. And there's a lot of people out there that need people to do Maps API mashups. Just even on Twitter, you can find lots of job offers. So now this is going to be a way where you can advertise in one central place that you're looking for Maps API jobs and prove that you're actually qualified because you've gone through all this criteria. So right now, the developer qualification is for Maps API and gadgets. But if this goes well with you Maps API developers, hopefully we'll have this for all of the Google APIs in the future. And so you'll be able to get qualified for everything that you learned about today and prove that you have really performant mashups. So that's it.